Good morning, and thanks for this opportunity to share some of our work at Charles River Analytics on Teledyne products. And we are very happy with the products that we have. We are using the forward-looking sonars, the P900, P450, and the micro bathymetry 2250, and of course the RDI, the Doppler velocity log. So what I will do is, given the opportunity, I will talk about some of the work that we do with these sensors and show how we could contribute some of the tools that we have developed on top of the sonar systems from Teledyne. So first, give a brief overview of Charles River Analytics, talk about some of our products which we use on top of the Teledyne products. We are basically a contractor for government, for especially our biggest customer is Navy. But if you are really interested in projects, I will be happy to discuss offline, talk about details. So I have picked few products that we have and which we are free to present today. But if you are interested in other products, I can always talk to our customers, get their public release versions. Talk about these products, and then also talk about underwater positioning system we have put together along with the RD instruments, the Doppler velocity log, for a very, very cheaper price. Compared to the expensive INS systems, we have got 10 times less, but accuracy is close to the expensive sensors, but not there. So that's what I'm going to do. So Charles River Analytics, which is located in Boston, Cambridge, Massachusetts. We are a small company. We have over 150 employees, but we are primed for a few programs. The focus is more on robotics, sensor processing, decision management systems, human factors, cognitive modeling, etc. So you can see that we have a spread of technologies, and the focus that we have in the Teledyne products mainly is for the undersea marine robotics area. We build our own underwater vehicles, large vehicles for the government. We provide we develop commercial systems under the SIBR Phase 2 programs. They are mainly using vehicles like Remuses. And we do a lot of signal processing, so that's where the image processing comes in from the blue wave or the Teledyne forward-looking sonars. And we are basically not fundamental research organization. We bridge between fundamental research to prototyping. So it's like TRL 5, 6 kind of prototyping for different applications. We have a facility in Rhode Island, which we actually operate, and we build most of our large underwater vehicles, and we operate, and we have the luxury of having the Navy test range close by. And we have offices in California and Pennsylvania. We operate remotely as well. As you can see, our customer base is mainly the defense, and we get projects from DARPA, ONR. They are our biggest customers developing underwater systems. So I will be happy to talk about some of these programs offline, but today I will talk about some of the commercial products that we build on top of the Teledyne forward-looking sonars. I don't know whether it is very clear, but what you see on your right side is a forward-looking sonar mounted on a Remus vehicle, and as it moves, you will see that it there are blobs appearing here and there will be a target. With high confidence, we build a track. So it's not that clear, but the idea is to use our tools that we have built, especially the vision kit, to use it to process forward-looking sonar and identify certain targets. Like, for example, if you are looking for a mine-like object, you pick that object and then to do a debris field detection, for example. Or it can be a mine, floating mine that you want to avoid, so obstacle avoidance. And all this detection and processing is to aid navigation. So we build a lot of autonomy for autonomous underwater vehicles. We have different behavioral approaches. What we do is based on these sensors. We have a suite of behaviors which are competing for the navigation of underwater vehicles. So we use predominantly the P900 and P450 for forward-looking sonars for navigation. And we also have SWAT type of imaging sonars like the MB2250. So these are some of the applications we are looking at for mine detection, debris field detection. So another application is using the P450 is to determine, which is very important for the autonomous underwater vehicles, to find out the trajectory, to estimate the trajectories and to identify the terrain that we are operating. So what you see here in this video is that the algorithm in real time using the forward-looking sonars and the microbathy, we actually generate real-time bathymetry and trajectories based on the bathymetry for the navigation of autonomous underwater vehicles. So we work with the point cloud. So what we do is, even the SWAT, we generate point cloud out of that and estimate the bathymetry and we generate the altitudes and also the trajectory for the vehicle to navigate. Feel free to stop me. I'm just going through the products that we built on top of Teledyne, mainly the blue wave sonar systems. Another application that we have with the P900 is, you see this ROV, we have mounted the P900 sonar looking forward, and we have a stereo camera system mainly for ship hull inspections. So the idea is that without using a Doppler velocity or a long baseline kind of positioning system, can we make use of the forward-looking sonar to estimate the pose of the vehicle. So we use the simultaneous localization and mapping techniques to use the sonar images to match the features that we obtain in consecutive frames. So that will tell you how much movement that you have made. So if you are looking at a ship hull, you can start from one location and then you can estimate your pose and you know where you are with respect to the ship hull. And the stereo cameras are used because in most of the inspections you want to visually see, and we process the image for visual depth as well. So we combine this forward-looking sonar and stereo imaging in order to estimate the position. So it's the pulse system, precise underwater localization using sonar and electro-optics. So this is a TRL6, and we are looking for collaborators. This is a CIBER Phase 2 project, and we have demonstrated of the Rhode Island facility that we have, and we are actually looking for ship hulls to go inspect and then to demonstrate the system. So as I mentioned earlier, the whole idea is to bring all this on board for autonomous underwater vehicles so that we can have reactive behaviors. We can react to whatever the targets or the features that we see, landmarks that we see. And one of the debris detection projects that we do with this system is that we have the blue wave Teledyne forward-looking sonar MB2250, working at a longer range, detecting debris fields. So the idea is that if you see man-made objects, you will see straight lines, circles, well-defined geometric shapes. So if you see many hits on geometric shapes, that is the area that you might have something interesting. So to react to that, get the AUV close by and do high resolution sampling and use visual imaging to identify the target. So that's one operation scenario. So when we develop these tools, we have our own tools that we have for visualizing, like the ProViewer, for example. I will just quit this and let me see whether I can pull up the. So this is the view of our multiview tool, which actually I will just look at one head from the SON files that we get from Teledyne sonar files. If I run this, you will see that in real time we can see, like the ProViewer, we should be able to see individual pings as well as navigate the point cloud. So to see how the point cloud work, and also you have a waterfall here. So if you are interested in a certain feature, you can create markers as you go on, and then you can analyze certain areas. So you can jump to the markers, and this is actually off San Diego. We collected some data using the P450. So you can see individual pings. So these are some of the tools that we build on top of the Teledyne product. So in real time, you can get some idea of the pose, the roll, pitch, and the position of the vehicle as well. So we have these tools, and we are looking for partnerships once again. So this is an alpha product, and whoever is interested to package this along with their products, we are happy to talk about that and to see how we could share the API. So let me stop here, go back. And for the same tools, we have built mosaicking tools. Oops. For some reason, actually you see the mosaic here, but I don't. Can we get the lights down? Is the lights down? All right. So the let me see. Yeah, it's difficult to see. What's happening is that this is a ProWave display of as you move the forward-looking sonar, and what you should see is the entire region that you observe. So we generate a mosaic. We have a tool which, as you move, which will generate a mosaic, and you can get a better idea of the entire operation area. So we have this tool linked along with the multi-view tool. Actually, it comes really nice on my display here, but unfortunately, you cannot see the complete mosaic. So, but you can see part of it. So what we do is we actually get the features, we stitch them together based on the pose of the vehicle that we estimate. So in order to do that, of course, you have to know where you are. So underwater positioning becomes very important. And there are INS systems, very expensive systems in the market. And for our strategy is that can we build a cheaper, when I say cheaper, I'm talking about the range of 5K or 10K. So we built this is also a SIBR Phase 2 project. We built this for the Navy, and now it's in the commercial product, Camino, combining aiding sensors with multiple IMUs. So what we do is we combine cheap IMUs. They are noisy, so you put it in a certain configuration. You put them in a configuration, and you process them, you try to capture the best out of individual IMUs, and if there's noisy, you should identify that there's a noisy sensor. And also the way that you mount the IMUs, you can get rid of some of the biases that you have. The interference due to magnetic or electromagnetic interferences can be cancelled out by putting the IMUs in a certain pattern. So what we are trying to do is, by looking at the accuracy and the accuracy and also how expensive it is going to be power-wise, size-wise, etc., can we get something out of here? So we know that there are expensive, high accurate systems, and if you just put an IMU for dead reckoning, you don't get much of the accuracy here. So can you build something here? So this is our motivation. And just to give you an idea, so what we do is we combine multiple IMUs, and this can go on. So in this case, we have 3 IMUs, and what we do is we use a method called hierarchical particle filter. It allows you to estimate the pose of the vehicle and then to optimize them by combining them together. And also with the Doppler velocity log, if you have a reamer system, for example, you have a DVL mounted on the vehicle, so use that speed information to strengthen the confidence of your post estimator. So this is one example, and we actually did certain runs, and you could see that if you have complex parts, that a lot of turning, diving, you can achieve about 0.4% of deviation, and so on. So I have a comparison here. We actually compared with the XC fins, which is considered to be expensive, and the system is able to achieve 0.1%, and our system can achieve it could achieve 0.2%, and the price difference is, when I say very high and low, we are talking about the order of 10 times less than XC fins. So this is another product that we would like to share. For example, mount it as a suite of sensors with the forward-looking sonar and the Camino together, and we provide the underwater positioning. So these are some of the products that we build, and in summary, so this is for the Camino. Once again, so it's basically comparing with fins, which is considered to be high accurate, expensive. We are able to get somewhere close by. It's not accurate as the fins, but not expensive as the fins either. So in conclusion, our focus is to develop technology for autonomous underwater vehicles and underwater adaptive sensing. So I think today the keynote speaker gave us a very good overview of the importance of having adaptive ocean sampling networks. And we operate with many customers. So we have some of the work with the NSF folks on adaptive ocean sampling. So how do you make your autonomous underwater vehicles adapt to these changes in the environment? So in order to have the autonomy, you need sensing capabilities, and we are using Teledyne products. We are very happy with the imaging techniques we have, and then we build a technology on top of that. We are really excited with the P900 because it gives you the point cloud, three-dimensional capabilities, and right now while I'm here, my team is collecting some data with the P900, developing testing algorithms. So we have also developed, as I showed you, the multiview tools, which will enable you to visualize data in real time, and also to have capabilities like mosaicking so that you have a better idea while you operate. So these are some of the products that I could talk about, but there are many, many products, especially the ONR UCCI program. We are one of the primes for the UCCI program, and I'm happy to discuss any topics that you would like to discuss. And these are my contact details, and feel free to contact me. Thank you.
Teledyne Marine. Everywhere you look.